This is the start of Chapter 30, Nuclear Physics. Today we're going to talk about the nucleus. We will, I'll show you how to find the number of protons and neutrons in an isotope. We'll calculate mass, defect, and binding energy, which go together. And then we'll talk about the strong nuclear force. So if you're writing this down, this is a lot to write, so just shorthand it. Again, it's a story, so just kind of a couple of reminders to help you with the story. Not really tested on this. And now I know a lot of you will remember some of this from chemistry. So we're talking about the nucleus and we're approaching it from the physics point of view. So you can use that chemistry knowledge to help support this information here. But again, this is more physicsy stuff. So what you know in chemistry can apply, but it's not the same exact thing. Because we're talking about energy usually, and not like chemical reactions. We'll talk about nuclear reactions. Okay, so Rutherford, you guys remember Rutherford? He's the one with the gold foil experiment. He shot positive alpha particles at gold foil, and he found that they were deflected, meaning that there was something positive in there that was fairly dense in the atoms that was causing these protons, these alpha particles, to be deflected. That led him to and him and a team of scientists towards the nuclear model, saying that there was something dense and positive in the center of the nucleus. But when they did this calculation, they knew what the mass of a proton was, and they found the mass of an atom, and they noticed that it didn't add up. If there was 2 protons, there was more than 2 protons of mass in the atom. So in 1932, James Chadwick, he actually found a neutral particle that had the same mass as a proton, but it was neutral. So that made up for the missing mass of this atom. They now knew that if there was 2 protons, there was also 2 neutrons. So the mass of the protons plus the mass of the neutrons ended up equaling about the same mass of the atom. And I'll tell you why it's about in a little bit. Alright, I'm going to move on again. It's just a story. So we're going to, just a little reminder of the different things that it's talking about in the periodic table. The stuff that pertains to us is the atomic number. This is the number of protons in the atom. Remember, the protons makes up the element. If you change the protons, you change the element. We're going to use this atomic mass unit. So the mass of one proton, which we say, okay, mass of one proton is 1 in atomic units. And the mass of a proton is equal to 1.66 times 10 to the negative 27 kilograms. So that is a conversion for you. If you want to convert from kilograms to mass units, that's what you use. The other number that you see when we write these elements is the mass number. So we have the atomic number and the mass number, which is Z up here. And it's the number of nucleons, which is protons and neutrons in the atom. So let me just write a little example for you. We have 4 nucleons, this is your mass number, and 2 protons, which would be the atomic number. So this is A, and this is Z. This means that there are 2 protons, and if there's 2 protons, then 4 minus 2 gives us 2 neutrons. Now, for lower numbers like this, you're going to see that protons and neutrons are pretty much the same number. But when we get up to higher elements, more neutrons are required to hold the atom together. So this won't always be exactly half. Now, the nucleus is very massive compared to the things surrounding it, but it is very small compared to the rest of the atom. So it's massive, but tiny in distance. It's a bunch of mass all crammed into one small space. That's what we're trying to say. If the atom was the size of a football field, and that's all your electrons spinning around there, the nucleus of the atom would be a marble. So that means there's a lot of space for these electrons to be zipping around in. And remember that atoms don't just orbit, they have wave properties, so they kind of do weird probable areas where you can find them. All right, let's look at the differences in these numbers. Your periodic table is located on 916, and that mass number at the bottom is a decimal, which is kind of strange because you'd think if helium has 4 nucleons, then its mass number should be 4. But what they do is they take the average of all the elements and its isotopes, and so you have some that have 4, but some that have 5, and they say, well, this amount of percentage has 5, so if we average it, we get a little bit more than 4. And that's where that decimal comes from. Even though you can't have, 4.2 nucleons. You either have 4 neutrons or you have 5 neutrons. You can't have half a neutron. But that's where that decimal number comes from. And the other thing that changes, especially for us that's going to change, is the number of neutrons and protons. If the proton changes, it changes its element. But if the neutron changes, then it's called an isotope. Neutron changes, you get an isotope. And one little vocab word that they have in your book, but I'm not going to use it very much. It says the nucleus of an isotope is called a nuclide. Just a little vocab word for you. You won't hear me say it, though. So think about the center of the atom, made of protons and neutrons. According to the electromagnetic force, what do protons want to do when they get close to each other? Want to repel, right? You got protons, and they're both positive, and they go, whoa, we don't like each other. And they want to repel. So how come atoms in the nucleus don't fall apart? Well, neutrons don't have any charge, though.
So neutrons don't?
Not electrically, no. We have the strong nuclear force. It is one of the 4 fundamental forces, which you've learned about 3 of these already. We learned about gravity, learned about electromagnetism. And today we're going to learn about the strong nuclear force, and tomorrow, the next day, we'll learn about the weak nuclear force. So gravity is the weakest. It attracts masses together. Electromagnetism attracts or repels things of charges. So electromagnetism is the reason you're not falling through your seat right now. So electromagnetism is stronger than gravity because I can break gravity just by jumping, right? Not very strong. But electromagnetism, that's kind of what's holding. It's the reason I don't fall through this table because the electrons in the table repel the electrons in my hand. Then we have the strong nuclear force, and that's the one we're going to learn about today. It is the strongest of all the forces. The problem with it is it's very, very tiny. It only acts within 56 nucleons wide. Nucleons being protons or neutrons. So if you have a ball of 56 protons and neutrons, that's how wide this strong nuclear force can act. Anything wider than that, and it's like stretching the rubber band too far, and it doesn't stay on very well. So when you get protons, and you have to give it a lot of energy to push these protons and neutrons close enough to get them within the 56 nucleon range, but once it gets there, the strong nuclear force binds them together. And this is called binding energy. It's the energy required to bond these protons and neutrons together. Our energies are negative, and that's because it's going to absorb the energy. And actually, it's because some of the mass is lost in that process and converted to energy. So it loses energy. That's why it's negative. Now, binding energy might seem familiar, or might not seem familiar, but the equation is E equals mc squared. You've seen it all over. You had no idea what it meant. You knew that it had something to do with mass and energy. But this is how you use it. You have energy equals the mass times c squared. So this equation converts mass into energy. Einstein was, I believe, the first person to link mass to energy. It was revolutionary. Now, when we talk about binding energy, it's not that we're converting the entire atom into energy. It's just a little bit of mass is lost when we bind them. And that amount of mass is converted to energy. So that's why the atom loses it. With the units here, normally we would do energy in joules, mass in kilograms, and speed of light being meters per second. But for your homework, because the masses of protons and neutrons are so tiny, they actually use it in U, which is atomic mass units. So if your mass is in U, which I'll show you how to do this, you just multiply it by 931.49 c squared, and energy ends up being in mega electron volts. So it makes the equation a little bit simpler. So you'll have mass in U and just multiply it by 931, and then you'll have your answer. Okay, so as I was saying, when you have nucleons and you bind them together, so you have protons and neutrons, and when you get them super close, they lose a little tiny bit of mass. And that little bit of mass that they lose is called mass defect. And this is the mass that you put into E equals mc squared. So you have to calculate the mass defect first, and then you can find the energy that the atom gives off. So normally you would think 1 proton and 2 neutrons would equal 3 atomic masses, because you have a proton and 2 neutrons. But when you bind them together, that is the little tiny bit of mass that's left, and you would end up with something like 2.88 U. So to find the mass defect, you take the mass of the atom, you subtract the mass of the protons by themselves and the mass of the neutrons by themselves. And you're going to end up with a negative number, which is why binding energy is always negative, because the mass has decreased. All right, let's look at binding energy compared to the number of nucleons. On the left, we have energy per nucleon required. And on the bottom here, we have the number of nucleons. So for the first one, you have 0 nucleons. It's going to take 0 amount of energy to find them. As it increases, 1, 2, 3, and then we get to 4, like helium requires, it has a bit of binding energy, a little over -7 megaelectrons. And then it goes, pops back up, and you end up with this nice little curve-ish thing up until about iron, which is going to be the highest energy, the highest binding energy, and then it kind of slopes off. So this is the most stable atom. That is iron, and that's because the strong nuclear force only acts within 56 nucleons. So anything bigger than 56, the neutrons and protons are just kind of tacked onto the outside. So overall, it makes the atom fairly unstable. All you really have to do is send another neutron at it, and a lot of times it'll break into a couple of different atoms. So anything over iron can undergo radioactive decay. And radioactive decay is just taking these larger nucleuses and breaking them apart so they become more stable. Okay, so here's my last little informational slide before we get to the clickers, and it says elements with a mass number greater than 56U take only a tiny bit of energy to lose their neutrons and protons because they become stable. And this is radioactive decay. So it's easy to make them unstable. All we have to do is smash, and we usually smash neutrons into them because neutrons are electrically neutral, so they don't get repelled by the protons, and they're not messed up by the electrons in the atom. They just can head straight to the nucleus and tack onto it and cause it to break apart. And again, this happens for things larger than 56 nucleons. I think I have 6 clicker questions for you today. A couple of them are easy and a couple of them are calculations, like what's going to be on your homework. Okay, here's your first clicker question. It says the strong nuclear force is blank. I got about half the class to answer. Couple more people. All right, if you didn't get a chance to answer, you should answer now. I'm going to end it. Okay, here we go. The strong nuclear force. It is the strongest of the forces, so it's going to be stronger than any of those, the electromagnetic force, but it has a very short range, so C is the correct answer. Question 2. This is like something you're going to find on your homework, so you should definitely pay attention to this. It says the phosphorus isotope, and it says 31 nucleons and 15 protons, has a mass defect of... So mass defect, I'll call it MD, negative 0.282253U. It wants to know what is its binding energy.
The 931 right squared.
Yes.
Like in the beginning of the year. Huh? Like at the beginning of the year. It was yesterday. Why? In the middle of the year. Because like a lot of people do stuff like that like in the beginning of the year, like rip off a piece of paper or something like that, and then decide like that's what. Mariah. Can you remember that? Can what? Can you remember that? What did she do? Just cut the whole class with fingers.
All right, we got some answers. Anybody else want to answer? All right, I'm going to end it. Here we go. So you're going to take this number and you just multiply it by 931, and you should end up with 262. Remember that binding energies are negative because the mass is lost in this, making it negative. Question 3. Calculate the mass defect of helium, which has a total mass of 4.02602 U. And it gives you the mass of a proton, and that's the mass of a proton and electron together. And then the mass of a neutron. So I'm going to show you how to do it. Don't freak out. It's not too hard. So we have helium, which means it has 2 protons, and there's 4 nucleons, and 2 of those are protons, so it's going to have 2 neutrons. Now the proton mass, and this is proton plus electron mass, is 0.007825. This is a constant, so you need to write this down for your homework. And then the neutron mass is 1.008665, and these are again in U. So this is the total mass that protons and neutrons have when they're not bound. So you're going to get some sort of mass. Call it M. So calculate the mass defect, which I'll call MD. You're going to take the mass of the protons and neutrons by themselves, which is this number. And then you're going to, oh no, I did it the other way around, sorry. I erased it. You're going to take the mass of the atom, 4.02602 U, and subtract this mass. And whatever you get for your answer will be the answer up there. Now it should be negative, because again, mass defect. Yeah, I'll do it right. end it. You should have ended up with negative 0.00696.
Will you quickly? So for the protons and neutrons, you multiplied each of them by 2 because
there's 2 in there.
Okay.
This one says has 2 protons, 4 nucleons, so 2 of those are protons, and the other 2 must be neutrons.
Okay, so like let's say it was a 3, you'd multiply them.
3 what? 3 protons, 3 neutrons. Okay. Okay. Let's say, not that this really happens, but let's say this is 3 protons, which means this would be something else. Then you'd have 3 protons and 1 neutron.
Okay, that's all I needed to know.
Okay. Okay, question 4 is a numerical one. And it says the mass of tritium is 3.016049 U. It has 2 protons and 1 neutron. The mass of an electron and proton together is 1.007825. That's a constant. And the mass of a neutron is 1.008665, which again is a constant. What is the binding energy of tritium? So I will help you out here. We have a 2-step problem. First of all, you need to find mass defect, and then you can find binding energy. So we have mass of an electron. Okay, it has 2 protons and 1 neutron. So it's 3, 2, which would still be helium. So you have 2 protons and 1 neutron. That'll give you mass defect. Once you get mass defect, or no, sorry, that'll be just mass, not mass defect. That'll give you the mass. So you're going to find mass defect by taking 3.016049 U and subtracting the mass that you just found. That'll find mass defect. So find this number, plug it in here, and then you can calculate the binding energy by doing the mass defect times 931. So this one goes in here. Now remember that binding energy is always negative, so when you type it in your clicker, make sure you make it negative. There's a positive negative button on there.
How many digits do you want?
Everything that shows up on your calculator.
Is this the same kind of test, or is this something you want to do?
I think it's conceptual stuff that's on it, but I don't think there's very much. Like 1 or 2.
And it's just a semester?
Yeah, just.
Is this stuff going to be on the same test?
I don't think it is, but it's been a while since I've seen the test. But I don't think it is.
You make it, right?
I make it, but I made it for you.
Are we allowed to have a cheat sheet on that?
Yeah, you have a piece of paper from that.
When are we starting? Are we starting that tomorrow?
For the juniors, you start next Wednesday after the test.
Oh.
So I still have 2 more days to teach you.
Are we doing the lab on
All right, I have a couple answers. I'm waiting for a few more. Anybody need more time?
Like 2 seconds.
Like 2 seconds. Okay, I can give you 2 seconds.
No, I said you're going to. I never said that. I want you guys to get into my show. Yeah, I'm sorry.
Make sure you put the negative in.
You can go. I'm just not going to answer you.
All right. Here we go. I believe it's like 7.69 or something.
Oh, that's right.
You gotta make sure it's negative, and it falls within that range. That says 7.78, but I got 7.69, which is fine.
I
It
got
falls
it,
in
and
that
then when
range.
she said make sure you add the negative, I was like, did I add the negative? So I was like trying to like scroll to look at it. Wait, so it's 7.09.
It would be fine. It falls within the range of 0.3. Okay, question 5. What is binding energy? What is binding energy?
It has bind in it.